Okay, let's resume. Um, so basically what we do is that we try to reduce the matrix one by one, one at each time, okay? And you start with this kind of matrix, and um, sometimes I tell you, but even if I don't tell you what this matrix is, you can actually pretty much figure out whether this is a matrix of similarities or matrix of dissimilarities or distances. So the clue here is that you actually look at diagonal elements. So the diagonal elements is actually one. So basically, it's a similarity matrix, and typically the similarity or distance are symmetric. So you only need to look at half of them, and so you start with this kind of things, and this is 5 by 5, so there is no problem. So all you need to do is to reduce into 4 by 4. Okay. In order to do that, what you do is that you actually select the one with the largest weights, um, because it's similarity, which indicates that P1 and P2 currently it's a special cluster of 1 points are the most similar one. So you merge them together and you end up with some kind of new clusters. So you need to figure out these cells. And the last time we actually mentioned that um, these kind of things, for example, for this point 7, is going to be because it's between 1 and 2 and 3, right? So 1 and 3 is actually here, and 2 and 3 are here. So basically, you are looking at these two guys and taking the maximum. So the reason we take the maximum is because this is a single link, so it encourages people to link as long as there is a single way to reach them or connect them. So perhaps more complex thing is actually this one. So again, in this 4 by 4 matrix, we actually decide to merge 4, 5. So whenever you have 4, 5, I think, yeah, this is the most complex one. The most complex one is actually this guy, because essentially now it's actually one between 1, 2, and 4, 5. So last time we mentioned that the simplest way is really to go all the cross cluster pairs. So you got four, right? 1 to 4, 1 to 5, 2 to 4, 2 to 5. Um, and if you are familiar enough, you actually can think about the maximum and min. They are um, you don't need to know each and every part. You can actually do the maximum min in each subsets and then take the min or max. Okay, so that's a special property of the min and max. Right, so give you a more simple example is minimum of a set of, let's say, 1, 7, 2, 6, right? So what you can do is that you can actually say these two are a subset. I take the minimum, but this is always the same as the minimum of the two guys, where the first guy is the minimum of 1, 7, and the other one is the minimum of, again, I'm talking about min. Here we are doing the similarity, so it should be max, but the property is the similar. 2, 6, right? So you take, the min on each and every subcomponents, and then take the min between the like subtotals or sub maximum or minimum. That's going to be the global minimum. Okay. So with this kind of property, you can see that basically I already know this value. This is the minimum between 5 to 1, 1, 2. Now the only thing is that now you have 4 to 1, 2. So basically what you do is that you actually take the maximum in these two guys in order to derive this guy. Okay, so that's a shortcut, if you can understand. Otherwise, go with the definition. We talk about, okay. Essentially, you try all these four lines and look up the value and do the maximum. I mean, so um, the complete link algorithm is actually very similar to this one. It's essentially always take the maximum between the dissimilarity. So if we use the similarity, which is the case here, we should actually use mean. Okay, so that's the main reason why I actually use a similarity matrix, just to emphasize that it's better not to remember the algorithm as min or max. Although sometimes we have to do, but in many cases, for the so-called max version, it's actually called complete link, and the um, short name is actually C-link. So we look at exact the same input. Okay, let's see how the result will be different. So what's going on is that in in the first step, you always choose the one with maximum similarities. So that's, you see, that's always the same, and you will see the same thing in the subsequent step as well. So what you need to do is that you need to merge 1, 2, and so basically you need to have 1, 2, and similar to previous method, you actually need to compute these three values. Okay, so the first value, so let's pick one of the values. Let's say 1, 2, and 4. Right. So you actually need to compute what's the similarity between a new cluster consists of point 1, point 2, and another cluster consists of point 4. So if we do it slowly, basically that's going to be, this is point 4, this is point 1 and 2. So you actually got two edge, right? So you have 1, 4, 1, 4 is 1, 4 is this one, 0, 6, 5, and 2, 4, 2, 4 is actually this one, right? 2, 4, 0, 6, 0, 0.60. So again, the complete link actually disencourage uh, merge. The sort of like you you merge because the worst case is actually the smallest so far among all the cluster pairs. So in this case, because these are similarities, so you actually pick the minimum of them. So that's why it's minimum of these two guys. Or graphically, you can see that essentially you locate these two values, then take the minimum. And you do the same thing with everything here. So you're filling all these values. And in this case, that's all you need to do. Then the next step is very similar. Okay, you enter into a new iteration. What you do is that you need to reduce 4 by 4 into 3 by 3. So what you do is that you always pick the maximum one. Okay, if you look at all the cells here, let's say if we remove all the marks, so basically the closest cluster at this time is actually between P4 and P5, which give you 0.8. Okay, the choice in this simple example happens to be the same as the min or the single link actually made, but the logic, or it's just a simple coincidence. Um, so in this case, we need to decide to again merge 4 and 5. So I think let's look at this one. This is the most complex one. So again, we should choose the minimum value of the similarities. So if we know, we already, this is between 1, 2, and 4, and 1, 2, and 5. Right? So 1, 2, and 4 is actually here. 1, 2, and 5 is actually here. So you actually take the minimum between 0.6 and 0.2, which give you 0.2. Okay. Of course, you can use this is a shortcut way, but you can use the standard way to do the calculation. So basically, again, although the merging decision, yeah, I forgot to mention that why we don't do from 3 to 3 to 2 by 2. This is because essentially we know, for example, in this case, the next one to merge is P3 and P4, 5. Unless you need to draw the dendrogram on the bottom right. Otherwise, you already know, dendrogram actually requires the exact threshold, the values where you actually make the merge decision. Okay, but if you, for example, if we don't mark that or we don't draw it proportional to that particular values, then it doesn't affect the results. Okay, in most cases, we only care the membership of the points into the clusters, and we don't really care too much about the um, the actual values, although it's still very useful information. So then from three by three, you can actually end up with 2 by 2 matrix, right? And 2 by 2, you actually identify the largest one, you go to 1 by 1, but that's like a dumb choice. If you want to have one cluster, then everybody is in the cluster. So that's why we stop at the 3 by 3. So for the strength of the max is that if you remember, the original points roughly form two clusters, but last time we actually added some kind of noisy points in between. And if you remember, the single link will actually eat into the larger part. Okay, but this is no more in you know max or complete link, where even with the noise, it tends to be, I think it tends to be this cluster and this cluster. So roughly speaking, it's more robust to noise and outliers. Okay, so it's less susceptible, but again, if you really have a lot of noise or noise with significant strength, it could still lead to unreasonable clustering results. Again, the problem with this kind of thing is that it's in high dimensional space, you can't visualize it easily. Okay, so it's really like for different applications, there are different ways to visualize or to understand how good your cluster is. Okay, either you have certain ground labels, ground truth labels, or for example, in some cases, we actually each dot is actually a document, and you can read through the document within the same cluster and see if they are coherent. For example, they are all about a topic or a style or whatever in a general area or genre, right? So the limitation of the complete link is that it cannot deal with the case where two clusters are close to each other, but one is much larger than the other one. Okay, so so for example, for humans on the left hand side, we believe that these are obviously two clusters. One is here, and the other is actually the other four, right? So, but the problem is that if you are going to form this kind of cluster, if you are going to form this kind of cluster, right? So up to a certain stage, you will actually see that before we form this one, you can actually see that, for example, this point um, and this point, for example, this point previously belonged to this small parts, right? And you can actually see that um, these two are actually closer to each other, but if you consider, for example, merging, so let's say C1, C2, and C3. Let's say before we reach two cluster, that's the configuration. So you can actually see that the complete link will actually see, okay, the the distance to merge, the distance between C1 and C2 is actually determined by, let's say, this pair of points. But between C3 and the C2, it's most likely it's going to be, let's say, this point with this point, which is actually a long distance away. So you can see that actually C1 and C2 will be merged together, then finally with C3. Okay, so that's the main reason that the end cluster will look like, I think it's somewhere here, and the rest is actually another cluster. Okay, so it will eat into the large one. So it tends to break large cluster. It's really hard to form a large cluster because the diameter is much larger, and it's biased towards a globe globular clusters. So it's more like a spherical ones. So the last one we talk about is actually the group average. So the group average version, uh, as we mentioned, the general idea is that all the previous method only depends on whenever you consider the clusters, only one pair of points, I mean the distance of one pair of points determine the similarity of the entire two cluster. So to some extent, it's not good, right? Not everybody have certain, I mean, to some extent, everybody have certain say in this process, but again, it's you can also argue that only one pair determine the final value. So an obvious idea is that you actually consider all the uh, let's say pairwise, or this kind of pairwise links, and then take the average. But it turns out that it will result in some kind of so-called inversion problems in certain cases, at least in the worst case. So we won't illustrate this um, further, but suffice to say that you can consider a real example where you have this D1, the coordinate is 1, 1, D2 is 5, 1, and this is 3, 4.5. And if you run the average version, you will actually see that they actually merge, they choose to merge D1 and D2 first at the distance of 4, and then to merge this cluster C1 and D3, the distance is actually only 3 point something. Okay, you can see. So basically, if you draw the dendrogram, that's going to be like this. Okay, so this is pretty bad. I mean, we do naturally prefer this kind of things. This is actually makes more sense, right? So in order to fix that, essentially we also need to take into consideration, all these kind of within the same cluster. I mean the similarities or distances. So you can think about this group average as group first, then do the average. Okay, this probably help you to understand what's going on. So in this view, essentially you actually group everything into one single cluster and take the average distance within any possible pair within this cluster. So mathematically, that's the formula. This is a very general formula in the sense that it actually consider PI. It actually works even if the similarity is not symmetry. Okay, so PI, the similarity between PI and PJ does not necessarily need to be the same as the similarity of PJ and PI. But again, in most cases, we will see very commonly symmetric similarity measures. So we don't necessarily need to follow this procedure. Just take the average of all the distinct pairs. That should be enough. Let's look at one example. So that's going to be the same example. And essentially what we do is that, again, the first step is to choose the one with the largest weights. And in this case, we need to merge 1, 2, P1, P2 together. So we need to form this guy. Right, we need to form this guy, 1, 2. And these three values are what we need to do. Okay, so let's pick, for example, this value. Okay, so this is actually between 1 and 4 and 2 and 4. So 1 and 4 is here, 2 and 4 is here. So if we run the round version, the value will actually be only 0 to 625, right? So that's going to be the average. So remember, we need to do the group first. So by grouping, it actually means we actually need to consider, um, you know, the distance between 1 and 2 as well. So 1 and 2 is actually 0.9. So essentially, this is going to be 0.9. Yeah, actually, I have yeah, I didn't illustrate this one, so it's good I write it here. So that's going to be 0.9 plus 0.6 plus 0.65 divided by, because there are only 3 edges, right, divided by 3. So if you do the calculation, it should be this value. So similarly, you can calculate all the other 2 values. And finally, we actually calculate, so this is actually 4 by 4. We actually need to further shrink it to 3 by 3. So again, whenever we have this 4 by 4 and need to decide to merge, our choice is to always seek the 2 which are closest. And this is similarity, so which means we need to find the maximum entry, which is actually this one. So again, the choice is still merge P4 and 5 together first, but this time the number is going to be different. So let's look at this one. So you create a new cluster which is 4, 5, right? And arguably, the most difficult one is actually to calculate the similarity between these two clusters. Okay, so if you draw it, it's going to be 4 points, and this is 1, 2, this is 4, and 5. So again, there are how many links are there? So there are actually 6 unique ones if you draw it like this. Okay, so between every two possible pair, or you can actually think you group them together into one group, and that's all the possible pair, right? That's essentially the same. So um, this is actually the procedure I mean, if you are not familiar, you can actually use this kind of procedure. Basically, that's going to be all the 6 edge weights. I mean, weights here are similarities, and if you follow the previous formula, that's going to be twice over all the possible edge, because each edge it's 1 4 and 4 1, like they think they are different. Okay, so it's almost like an undirected graph, right? It can be treated as, you know, having two edge on each of the undirected edge. You know, so but for most of the people, I think it's easy. You got 6 distinct pairs, and then you divide by 6. That's going to be the same, right? Okay. So many of the students actually, again, for this example, it probably works. But the problem is that if you want to do the same trick, you want to use the same trick, average of, let's say, 4 guys. So if you divide them into equal groups, right, where each group have the same number of points, then you can do the average. You can take the average here and take the average here, and then do a simple average. But the problem is that if, for example, this guy actually has 3 guys, right? If you divide these into these 2 guys, this average, and take the average, it doesn't, uh, equals the average of the whole group of 5 objects or 5 values. So in this case, you actually need to take into consideration the counts, the size of the group. So it's a simple exercise so for you to work out how to do it faster. But again, if you are not comfortable with this or can quickly understand how to modify this to work on average, then I suggest to follow this kind of procedure, which is by definition. So it's a little bit slow, but and a little bit tedious. But again, we won't give you large examples, and it's better to be correct. Uh, yeah, that's more important. So as you can see, essentially, because we are taking the average, again, for this example, if you forget about these two additional edges, basically that's going to be the average of the 4 uh, edges, while the single link and the complete link only take the minimum or maximum of these 4 edges. So to some extent, you can expect that, not surprisingly, this algorithm is a compromise between these two extremes. Okay, usually the value sits in between. That's why it sort of like have both the strengths and the weaknesses of the both. So it's less susceptible to noise and outliers if you compare with the complete link, but it's much better than single link. And on the other hand, basically, it actually inherits the weakness from complete link, where it's more like a globular clusters, but it doesn't have uh, it. I would say it's still kind of more closely aligned with complete links. Okay, but to a less extent, if you like. So basically, if you run this kind of things, maybe this time it will actually cut into here. Okay. Again, you still have this problem of eating into the large cluster. Okay, So let's have a quick look at the summary of the hierarchical clustering algorithm. So all the hierarchical clustering algorithms, they do not scale very well. So the time complexity is at least n squared. Actually, the single link and complete link actually are n squared. For the group average, if you know how to do the scaling, do the clever algorithm, it's also n squared. There are actually more, but if you don't know, then it's actually n cubic. So there are actually more complex hierarchical clustering algorithm using more complex criteria, and they typically are more than quadratic. So remember that quadratic is already very, very bad for large matrices. Okay, nowadays, if I give you 1 million documents, which is very common. Okay, think about clustering on tweets or whatever things. So basically, if n is 1 million, n squared is too large to be really computed. Um, so typically what we do is that we only use this for small amount of data because first of all we can afford to do that, and also the result can be visualized much better. Okay, but if you really want to use it for large amount of data, there are actually advanced algorithms which combines the hierarchical clustering with the sort of like partition based method. Okay, you can think about one of the methods is that you actually sample the points, and for the sampled points, you actually run the whatever your favorite HAC algorithm, and once you get the desired number of clusters, you actually select these kind of points or their membership as the initial centers. Again, there are procedure to find out the representative in, let's say, in the resulting cluster returned by hierarchical clustering. But once you get that, you actually use this as initial seed, and you can actually run the k-means for several iterations, but with the entire dataset. So that's another way to deal with it. Okay. Um, so next we are going to have a 10 minutes break. Then we actually move on to another very different kind of clustering algorithm called the spectral clustering.